We're going to put the t-shirts away soon, so if you haven't grabbed a conference t-shirt, you should go get one now. And just a reminder, if you're leaving, there's a bunch of Meta employees that are standing outside this room to escort you out. So just find somebody with a Meta badge and they can take you.
Hello, everyone. I am Natasha Sehgal from the Presto team at Meta, and today I'm going to be talking about probabilistic data structures in Velox. So for today's agenda, we're going to start with a quick introduction into what these are and the kind of problems that it solves. And then I'm going to go into the different probabilistic structures we have in Velox. I'm going to talk about the ones that existed versus all of the new ones that we added to complete the Prestissimo migration. And I know Amit covered on the Prestissimo journey, so I'll quickly go into what it looked like for these structures and how to test functions that do not return the same results every time. Okay, so first, what are probabilistic data structures? So these answer the questions above, but with some sort of probability. So instead of the exact answer, these return it with a small approximate error. So the reasons for this, so this minor accuracy trade-off is worth it in real-life use cases when you care about memory and latency. And one thing to think about is how much memory difference is it if you want to get the exact answer versus an approximate one with a small error. So this is what it looks like for the questions in the previous slide. If you wanted the exact answer for 1 million data points, the answer would be in an order of megabytes. And then if you wanted to get the exact answer for like 1 billion data points, the answer is in gigabytes. And now if you were to use a sketch, so a sketch is the main probabilistic structure that I'll be covering in this talk. And a sketch is a compact data structure that summarizes data. And so if you see here that its size is in the kilobytes, and it always remains the same regardless of your data. So as the data grows, the sketch will remain the same smaller size. And since it's a smaller size, you can divide it into parts, build partial sketches on different machines. And then since they're small, they can be cheaply sent over the network and combined on one machine to get the final answer. Okay, now looking at the different structures. So to solve the quantiles, we've had KLL and Velox. Two of the new structures added are TDigest and QDigest. And we've also had HyperLogLog. So I'm going to go into a couple of the new variants added. And these solve slightly different questions around cardinality. as well as in the space of set similarity and interesting questions about privacy. And I'm also going to go into a new version of the Bloom filter for membership problems. Okay, now for solving quantile estimation questions, such as what value is in the 95th percentile, or what percentile is a value. So KLL is a pretty standard way to solve these questions. It has strong error guarantees, and it's a good default in terms of performance and space. But we did add TDigest and QDigest for backwards compatibility with some of our Presto workloads. So just a quick introduction into what these are. So TDigest, how it works is it's a sorted list of centroids, so mean weight pairs. So you have different centroids, and you have more at the tails of a distribution rather than the middle. So this is good for solving questions around the tail end. For example, what is the accuracy at P9, or what is the value at P99? And then this compression is controllable. So you can have more centroids for more accuracy at the cost of memory. And now coming to another data structure that solves this quantile problem is QDigest. And this works slightly differently. So this is a tree structure which stores value ranges and counts. And unlike TDigest, this has a guaranteed error bound at any quantile. So you can configure the max error that you're OK with. And a lower error would give you more accuracy, but then the merge in the tree would be slower. One difference is since TDigest deals with division and averaging, right now in Velox we only support doubles, but you could add support for real, since float can be converted to double losslessly. And QDigest is working with counts, so it does support big int, and then real and double. So we just ported over whatever value types we had in Presto Java. Okay, so on the next topic of cardinality, which is for questions like how many distinct users visited a page. So HyperLogLog exists, and we added a variant in Velox. So I'm going to quickly start with the definition of what HyperLogLog is. So for calculating questions around how many distinct users, distinct numbers in a set, how this works is if you have a value, you hash it, and then you get a 64-bit output, and then the initial part, it decides which bucket it goes into. And in the second part, you count the leading zeros. So each bucket is storing the maximum number of leading zeros it's seen. And then you average over the buckets to get the approximate distinct count. And how this works is, if you think of like flipping a coin, you have to flip a coin a large number of times to get 10 heads in a row or 1,000 heads in a row. So you could think of 0 like flipping a coin and getting a head, if 0 is the head in this case. So what we added is P4 HyperLogLog for Presto Java compatibility. And this is a dense-only format. So one quick thing into the representation. So when your number is, when the number of values is small enough, you can have a sparse mode, which is wherever there are non-zero buckets, you store that bucket index and then the value. But then as you see more values, all the hashes or all the buckets will be populated. So then you can store it in a fixed array. So now you just have to store the value, and then the bucket index is the array's position. And in this P4 HyperLogLog format, this is only like the dense format. So you can extract out the minimum value. So the bucket value, to get back the value, it's essentially the minimum number, which is the baseline plus the delta per bucket. And then there's also some field for overflow, but this is unlikely. Because if you have a good hash function, then there is not as much skew. So this casts to and from HLL. If the HLL you're working with is sparse, then it's converted to a dense format first. Now building on HyperLogLog, we have two interesting data structures. One is KHyperLogLog. So this solves the same question, but across another dimension. So instead of just distinct counts, you're getting distinct counts per group. For example, how many distinct users does a zip code identify? And this is very useful in the privacy space because a common question is the k-anon or k-anonymity problem. So how this works is if you have, suppose, a group of users, and then there are very few users in a zip code, like less than or equal to some number k, then it is considered dangerous because you can re-identify the users if it's like a less number of users in a cluster. Fun fact, the k in KHyperLogLog is not the same as the k in k-anonymity. So what this K is, since we are storing the HLL per group, but as you get a lot of data, you're not able to store the HLL per group. So we only store HLLs for the K minimum hashed keys over here. And now the next data set is SetDigest. So this solves a cardinality problem, but more in the set space. So for example, what percentage of web users also use mobile? So this question is a set overlap question. Or if you look at how many users exist on both platforms, web and mobile, this is a set similarity question. So this uses the same data structures that you have in KHyperLogLog, min hash and HLL, and together it gives you the overlap count. So as we saw, HLL is cardinality, it tells you how big a set is, and then min hash shows you how similar the two sets are. So this is done using a Jacquard index, which is the union of sets divided by the intersection. But in these two cases, we use the minimum cardinality set because this also helps with like set containment if one set fully contains another set. And similar to KHyperLogLog, below a certain value, you get the exact answers. And above that, it uses these data structures to get the approximate estimates. So the next one is an interesting one, SFM sketch. So this is essentially HyperLogLog. So you get the distinct users, questions like that. But if you had the HLL sketch and you deserialized it, you could get back the users. And so what SFM sketch does, it protects users' identity. So SFM stands for sketch flip merge. So for some of the bytes, some of the bits are independently flipped with a given probability. And this is controlled by a value called epsilon. So that if you have a lower epsilon, you flip more bits. So this results in more noise and stronger privacy, but at the cost of accuracy. OK, now the last one here is not a sketch, but it's a very common probabilistic filter, which is the Bloom filter. And this is used for membership questions, such as, is a value in a set? If the answer is no, then no is always, no means no. And if the answer is yes, then it means that the value may be present in the set. So Bloom filter has existed, but last year we got a version of Bloom filter, which is called the split block Bloom filter, which is being used in a few meta production workloads. So this helps solve a problem of skipping rows that don't match a join. So how it's different is from the Bloom filter, it's just an optimized version. So the filter is split into blocks, cache size blocks, and then you can check if the bits of a value are in a block using SIMD in one operation. So this is used for dynamic filter pushdown in some meta workloads. So the example is if you have a hash join, you can push down the build side filters down to the table scan. And if the value never exists, there is no need to materialize it, and you can like skip it at the IO later itself. OK, so now on a different topic, now that we discussed a quick overview of the different data structures we added, is the testing in Prestissimo. And I know Amit covered this, but I'm going to just go quickly into some of the testing aspects that are useful for these data structures. So one is about aggregate functions. So also, as James said, geospatial functions was one of the last pieces migrated in 2025. And so are some of these data structures, like KHyperLogLog, and SetDigest. So some of the difficulties are when you're moving a data structure, it's not just the functions around it. You need to see how do you want to build it, how does the merging work, serializing, deserializing. And there were several aggregate functions as we're dealing with data at a scale. And with aggregate functions, you're processing many rows and returning one output. So in Presto Java, this is relatively easier because the framework handles inputs, outputs, its combinations, nulls, it iterates through rows. On Velox, there's a good framework to do this, but it's slightly more difficult because you're working with data at a lower level. With vectors, you need to handle like nulls, memory tracking, etc. So this can create more bugs, and there is scope for crashes. But the benefit here is you have a lot of control of the memory. You're not dependent on just like garbage collection. And you can do performance optimization, like some of the SIMD optimizers discovered, shared previously. And you can also do zero-copy serialization. So if you're sharing data to like another operator, you don't need to use any intermediate buffers, and you can directly write to its output. So one interesting production quirk that came up when we were moving some of these probabilistic structures is the hash functions. So the hash function does matter. So Presto Java uses a different hash function from Velox. So for prox distinct, we were able to use XXH64. This is a faster, more optimized hashing function. And since you're dealing with counts, it does not matter if the previous workloads from Presto Java used a different function. But for a prox set, since this returns HLL-digest, if you don't match Presto Java, what we saw happening was there was an overinflated count. Because if you use different hash functions, then a value is assigned to different buckets, and the results were not correct. So one thing we made sure when adding these data structures are, especially in the unit tests, is if you're able to take a Java structure and successfully deserialize it using the CPP library. And also if you take a structure generated from CPP and Java, and can you merge it together and get a valid value in the expected range. So the next bit is testing. So from the CI side, we have a comprehensive fuzzer structure testing framework in Velox. This is an E2E test for correctness. So based on the seed you give, each seed generates a different inputs for functions. And these functions can be inputs for other functions, so you can get various query shapes. And it can do a lot more testing that unit tests can do. And the other thing is for meta, before going to production, we have a verifier suite that we run. So it samples the latest production workloads, and then you can run it on our control cluster, which is the Presto Java, and then test cluster, which is our new Prestissimo cluster. And then we can compare results. And this can also be used for custom testing. So if you have your own build, then you can also select which queries you want to run this exact framework on. And this was pretty useful for probabilistic data structures, because for the outputs, if you're dealing with like a prox distinct counts, you can see that the verifier suite works as expected. But when the output is like in bytes, for example, merge HLL, if you're introducing a new data structure, it helps to like quickly go through some of the results and deserialize it, check if it makes sense, if it's in the ranges. So now going on to the fuzzer components that are relevant for these sketches. So one is the input generator. So if you had an input, like for example an integer, it's very easy to use a random generator, get an integer in the minimum or maximum range that you're interested in, the kind of distribution that you want. But for sketches, you need to be able to generate these inputs. So for example, for TDigest, you would take a distribution of doubles, the compression value you want, and serialize it to a TDigest structure to use. And the next bit is how do you do result verification when you have approximate answers. So you cannot do like assert equals to 2 or 3, some sort of integer like that. So we have two strategies for the result verifiers for these aggregate functions from probabilistic data structures. So the two strategies are, one is verification, where you verify against an independent ground truth. For example, if you're doing a prox distinct on a set, and you know the results from count distinct, you'd expect it to be in the same, like in an acceptable range, to say that a prox distinct is working as expected. And that's what we do. We do a similar thing for a prox percentile. And the second strategy is compare. So this is when you have a query, you can run it using different execution plans, and then do some sort of a semantic comparison. So for example, if you have queries with TDigest, QDigest, what you can do is you can run the same query on a single operator, or you can like create partial sketches and do a final aggregation and see if the results match. And then you can also try with and without spilling to disk. So one interesting thing over here is forgot what I was going to say. So what's next? So right now on the meta side, we do have folks still working on TDigest. It's being used. There are new functions going on. And we're always looking for different opportunities. On the Velox, there is one issue created for count min sketch. There is a requirement for frequency estimation. And fuzzer coverage, we're always looking to improve this testing suite. Like for SFM sketch, since you want non-determinism, maybe instead of looking at some sort of approximate values, it could be useful to check, run the same query plan, not just the same query, several times and see if the result makes sense statistically. Yeah, that's it. Thank you.